Hello and welcome. In this video, I am going to talk about the fundamental theorem of Galois theory. So I will be making 3 videos on this theorem because this is the main theorem of Galois theory. So in first video, I will be talking about if we have given the Galois extension, then existence of Galois group, which would be basically the group of the automorphisms which fixes the field F, which is fixed field. So in the converse part, I will be talking about if we are given the Galois group, then existence of Galois extension associated with it. And in a third video, I will be giving the correspondence between them. Okay, so let's start for the this proof that we are given your F is a Galois extension. So it is normal, separable, and of course algebraic. So any irreducible polynomial or F will have at most n roots inside E because it is normal. So there will be at most n automorphisms from n to n, E to E, E to E, which fixes the field, F. So what is the meaning of this automorphisms? That these are the automorphisms which will fix all element of F, and for the rest of the elements they will, so suppose sigma is automorphism, then it will fix all the elements inside F, and for the rest of element they will be mapped according to accordingly by the images of the roots. So suppose these alphas are the roots of irreducible polynomial, then these roots will be altered under this automorphisms, and the rest of the elements besides these roots will be generated by these roots. Okay, so that is the thing. So there will be at most n such automorphisms, and since also it is Galois, so it is separable as well. So the irreducible polynomial will split linearly inside E. So there will be n distinct roots. So there will be, what is that? What does that mean? There will be exactly n automorphisms. So exactly n automorphisms from E to E, which fixes F. Okay, so this n automorphism we call the group of these automorphisms as G of E or F, and this is the Galois group associated with this extension. So now I define the set E L. Okay, so L will contain all the elements in E which are fixed by all the automorphisms. All inside this group G of E or F. So obviously F will be inside L because F is what? F is fixed field. So fixed field means what? It contains all the elements which are fixed, all the automorphisms which fixes all the elements of F. So if there is any elements in each E which are not in F, and they are fixed by all the automorphisms, then they will land in E L. But we want to prove that this F and L are same. So by showing that, we'll get that the F is a fixed field for this Galois extension. Okay, so that is what we wanted to prove. So this inclusion is clear because F F is fixed field, and it contains all the automorphism which fixes the all elements of F, and L is the if there are extra elements which are in L, which are in E, and they are also fixed by all the automorphism, then they will end inside L. So obviously F will be inside L, but now I claim that L is also inside F. So if not, then for then if A belongs to L, consider A belongs to L, but A does not belongs to F. Okay, so A will belong to E, right? Since L contains all the elements of E, and A is not inside F. So A will be separable element. A will be separable element over F. Okay. So what will be the degree of A? So degree of A over F. What will be the degree of A over F? If it is 1, then what will happen? Then E over F will be of degree 1. So that is not possible. So A will have at least degree 2. Okay. So now consider a minimal polynomial of A over F. So this minimal polynomial will have a degree at least 2. Will have degree at least 2. And we have A is root of that minimal polynomial. So there will be at the 2 distinct roots, right? So this minimal polynomial have 2 distinct roots, and since this is the roots of same minimal polynomial, say b then another bbn, let b be n another root, then a is not equal to b, and a and b are conjugate. Then we know the theorem. So there exists a automorphism from f of a to f of b such that to b. Okay, and also there is theorem that this automorphism can be extended. So this automorphism can be extended to an automorphism sigma dash from E to E. So it can be extended to E, which is the extension of F, and A and B are the 2 separable elements inside E, and they are also algebraic over F. Okay, so such that so what will be the sigma dash of A? It will be again sigma of A. And what is sigma of A? Sigma of A is B. Okay, so sigma of A is B, so it cannot be equal to A. So this sigma dash is automorphism of from E to E, and its image, and A is a separable element in E which is not inside F. Then we got what? A will be not inside L, because what was the definition of L? L contains all the elements of E which are fixed under all the automorphisms from E to E. So we have got this automorphism which does not fix the A. Okay, so A was element from L. We have considered that A was element from N, L, which is not inside F. So here we got the contradiction that does not belong to L. Hence L contains F and L is equal to F. So we have started with the element L inside A inside L, which is not contained inside F. Then it will be in E. It will be separable element in E, and it will have degree 2 and the polynomial. The minimal polynomial will have distinct roots, and using these two theorems we have got that there is automorphism from E to E such that it does not fix the A. So therefore A is not belongs to L, and that is a contradiction. Therefore we got that L is contained inside F, so L is equal to F. Therefore what we can conclude that therefore there is no such a element in E which can be fixed under all the automorphisms from E to E. So what does this mean? That F is a fixed field. So that is what we wanted to prove. So therefore F is the fixed field. So okay, so in next video I will be proving the converse part of this. Thanks for watching.